you. Hello, hello, hello. Thank you, Asada. Good afternoon. Okay, so yeah, my name is Kwadwo. I'm with West Africa, and yeah, that's my face over. I'm a little nervous. Like PhDs and researchers at DeepMind have gone before me, so. All right, so a little about me. I went to Motown, from Motown to KNUST. I'm currently at MEST, and I was recently accepted into UC Berkeley to study data science. So hopefully by the end of the year, yeah. I mean, like even if I can't pay for it, I think I'm Berkeley material now. Yeah. All right. When I'm not coding or doing anything messed, I play the drums, I play the guitar, I play the keyboard, and I write on my blog. Yeah. It's bolding so that you can visit. The link is bolding so that you can visit it. Yeah. It's not all techie stuff. There's stuff there that'll make you laugh. So today we are talking about deep learning. Um, it's the fundamentals, right? The fundamentals, some architectures that you should know, and the applications. Fortunately for me, a lot of my work has actually been done by some of the previous speakers. So whatever you see here that was not in their talk is what you probably classify as a little advanced. Whatever you find here that was in their talk is fundamental. Okay? Makes sense. All right. So the first thing you should know is that deep learning is taking over. Okay. And I'm saying deep learning, not necessarily machine learning. Machine learning is doing a lot, but deep learning has a new dimension to it. But before I talk about that, I want you to see this video. How many of us are developers in here? Developers of any sort? Yeah, yeah, my people. So I saw a video like this and I said, no, I have to study machine learning. Because what is happening here is the guy is drawing wireframes on the board, and there's a camera looking at the screen, looking at the board, what he's drawing, and he starts to identify the various components, and is building out a front-end application. Okay, and if you're close enough, you see that it's actually a React application. It's not like raw HTML, CSS. The machine learning model is building a React application. Okay, so this, and I actually spoke to the guy who started this, the company that does this. It's called Tony Beltramelli. He lives in, I forgot, he lives in Europe somewhere. And the project has gone on. They are able to do the same thing for iOS and for Android. Okay, so essentially, when you talk about these things, developers feel safe. But if we do not adapt and study these things, there is the possibility that this will be able to develop faster than you, right? And you might be in trouble one day. Okay. So that was my personal motivation for entering machine learning. I'm sure we've seen this was in Doc's. This outline was in Doc's presentation before me, Dr. Kosa. So the question about who is whose father and whatnot. So from my perspective, artificial intelligence is like the grandfather, machine learning is the parent, and then deep learning is the child. Okay, and just as every child is supposed to do better than their parents, that's the order in which they are effective. Okay, so let's start from machine learning, like very quickly, because you can't talk about deep learning without talking about machine learning. Okay, so um, one of the main purposes of machine learning is that we want to take data, and then we want to use that data to answer some questions, what we call a prediction. Okay, this prediction could be classification, it could be regression. Classification is for discrete outcomes, regression is for continuous outcomes. Okay, so the main thing we need here is data. You take the data, you use the data to train a model, and then the model is able to do stuff for you, stuff that's very impressive. But the key here is data. Because like somebody defined in the morning, for machine learning, you are not explicitly programming the computer. You show it the data, it learns from the data, and then it does stuff with it. Okay. So in machine learning, one of the key things that anybody needs to know is gradient descent. Gradient descent is what I call the holy grail of machine learning. And the idea is simple. If you can take any problem and model it as a function, okay, you should be able to plot out a graph from that function, okay? And let's say the graph looks like, where's the pointer on this? So the graph looks something like this, okay? Now this function here is what we call a loss function or a cost function, depending on how you're looking at it. And so at the top is the area of the highest loss, and so the red area, and the blue areas down at the bottom are the areas of lowest loss. So what learning is essentially is that you are taking the model, like remember the example of the robot trying to flip the pancake, right? It tries the first time, there's an optimum output, and then there's the robot's attempt, the result. And the difference between the output and the optimum output, okay, in supervised learning, that's the difference between your label and your prediction is your loss. So the essence of learning is to reduce your loss. Anything you do to reduce loss is what we are classifying as learning. So the machine is learning in essence to compare its attempts with the loss and steps to reduce the loss. This is what we call gradient descent. So the same way you can be on the top on a slope and start moving down, where the top of the slope is the highest loss, the bottom of the slope is the lowest loss possible. You are descending the gradient of loss until you reach the optimum amount of loss at the bottom there. Okay, makes sense, right? So essentially, you have your training data. You have, yeah, I saw this formula this morning. You have some weights that are assigned to the your model, okay, and then based on some computations between the weights and the incoming data, you optimize and adjust your weights until you reach a point where you have the minimum loss. Okay. All right. Now the problem, so that's for that is generally what we see with all kinds of machine learning. So regression problems, classification problems, we find that there. Now the problem is that if you were to narrow down, or should I say condense this methodology, okay, where you multiply your input by some weight to get some hypothesis. The hypothesis is what we are, our prediction, right? It begins to look very similar to a brain neuron, okay? So this, if you remember your high school biology, you have the dendrite at the end there, you have a nucleus, and then you have an axon, which is your output. So inputs are coming in, going to your axon, and then going out. But then this problem here, okay, because you remember we said the foundation of machine learning, one of the earliest algorithms was linear regression, because so many problems can be solved by drawing it out as a straight line. Okay, so this here is a linear, uses linear output. But then very early on, people realized that there was a unique problem that was faced, which is that not all problems can be solved with a linear solution. Okay, so for example, this here is a popular problem called the XOR problem. It looks like a simple problem, but it's very complex. That's why I say a simple complex problem. Now, if there's anybody in this room who can draw a straight line to separate all the greens from all the reds, a single straight line, I'll give you my car. Granted, I don't have a car, but yeah. But it is impossible to separate the greens from the reds with a straight line. You can try with your eyes. Has anybody succeeded? All right, my car is safe. So we needed to find, I say we like I was there, we needed to find a solution that goes beyond just these linear solutions and do something that is non-linear. Okay, so what they realized was that if you can stack these, so this model is called a perceptron. Okay, so if you can somehow combine these perceptrons into a network, you are able to develop something that is a little more complex that can solve this. And so, yeah, this brings me to the idea of the universal approximator theorem. When you're able to stack these, okay, so from now I'm calling the perceptrons nodes, okay. When you're able to stack these nodes in layers, for any problem that can be modeled as a function, okay, any problem that can be modeled through whatever means to get a function, no matter how complex the function is, there exists a feed-forward network, a network of nodes like this, that can solve the problem, theoretically, okay? Now we say theoretically because the amount of nodes that you will need in the layers to solve the problem is infeasible. You run out of memory, you run out of computing power. But if you could get all the computing power or the memory necessary, it is possible to model any neural network, that any single layer feed-forward neural network that will solve your problem. All right? But because this is impossible, this is where we come to the issue where you need depth. So the universal approximator theorem is saying that this network here, if we could extend all the nodes so that we have so many nodes in the middle layer, we'll be able to solve any problem. But that doesn't make sense computationally. So what we do is that we then extend the nodes out in multiple layers. And this gives us extra complexity. It gives us higher dimensionality. Because the thing about, let me go back to this problem. For this, you are looking at it in a 2D space. But assuming this was in a 3D space, it's very possible that you could then get, let's do some imagination, right? So this, let's x1 be our x-axis, let x2 be our y-axis, and then imagine the third z-axis, which is depth. Now imagine that the two green were forward a little, like closer to you, and the red were back. Then at that point, it's possible to put a plane in the middle. So once you increase dimensions, you are able to solve some of these problems. So these deep neural networks are able to increase dimensions in the sense that what comes from the input over here entering this network here, you see they are densely connected in the sense that every node is connected to every other node from one layer to the next. So this layer is able to extract more features from here, and then the output from this layer goes into this layer as input, which extracts even more features, and it goes on till we finally get to the output. So that by the time you reach the output, you might have started with maybe 5 features, but the system is able to extract, there's actually calculations for this, but yeah, I don't want to make a bad guess. But the system is able to extract more features, which gives it essentially more information with which to solve your problem. Right? So we are able to extract more features automatically because it looks like magic, and we have higher dimensionality. Another important feature of these systems is that once you get a working model, okay, and machine learning is highly driven by research, as we heard a lot about research in the morning. So some smart people have researched various ways to do certain things with specific neural network architectures, which you can then tap into and use the same model to work on another problem. So a good example, you have a model that is able to identify lions, okay? You can take that model and then tweak, should I say, the ending, append your own model at the end, and now retrain that model to identify tigers. Because there are certain features that are synonymous with cats, those features can then be reused in another model which has just been tweaked a little, and then you get a model that identifies tigers, right? And that's the concept of transfer learning. So you take what works in one system, tweak it a little, it works on another system, all right? And then there's also end-to-end learning. So, for example, a good example is Google's Google Translate. Yeah. So what used to happen was that there were a lot of intelligent people who would sit down and analyze linguistics, analyze all the fundamentals of texts, and then try to derive some code that will do, and it was working. Like you can get what somebody is saying, but you can't have a conversation. Now the day they changed, and I'm talking about like literally the day when they switched to an end-to-end learning system, the amount of the score that they used to measure their performance, it increased exponentially. So what end-to-end learning is essentially you take a model, put it in the middle of input, output, and just let it learn its own thing without any interference. And as it trains itself on the model and goes on and on, it's able to derive whatever it needs from the input that is necessary to give it a good output. and then work independently of you, the developer of the model. Okay. So end-to-end learning and transfer learning are powerful tools in the arsenal of any um, machine learning engineer. Right. So under the hood, this is how it works. You have your input. It goes through. You remember the formula, the linear formula, y is equal to wx plus b. It goes through the system, each layer. So this will be our first layer. This will be our second layer. Some feature z is extracted. It moves on. This is just a two-layer network, but it moves on to whatever, how many layers, and then it gives us an output. Now, based on the desired output, which is the actual value that we are looking for, and then our predicted value, we calculate the loss, which I mentioned earlier, and then that loss is passed back through the system. Because you see, for gradient descent, it's easy to look at the loss and then know what is the next step to go to subtract actual minus predicted. You are able to calculate your gradient, you move another step. But in a feed-forward neural network, the difference in gradient between here and here might be different from that between here and here, and you never know until you reach the output. So once again, mathematics came to save us. We figured out that, once again, I say we like I was there. We figured out that when you take the loss and you propagate it through the system by the chain rule of calculus, differentiation, okay? So you know the way 1 over 2 times 2 over 3 is what? 1 over 3. The 2's cancel out. That is the idea of the chain rule in layman's terms. So you take the difference and you propagate it through the system by that chain rule, okay? So essentially, let's call this y and let's call this x. Dx dy is equal to d whatever dx times d whatever the second one, the first one. You get what's happening here. Okay. So the difference in this over the difference in this times the difference in this over the difference in this, and so on and so on and so on, till you get to the end, and you propagate your error through that, and as it goes, it adjusts the weights to give you a better output. Does that make sense? Right. So that is the what is the secret sauce, the magic, because it looks like magic a lot of the time. The magic that happens within these hidden layers, it goes through the first time, then it's propagated backwards by all this plenty mathematics you don't like to talk about. So the moving forward is called forward propagation, and then moving back through the chain routing is called back propagation. And then activation functions, I think they were mentioned extensively today. The most popular are the sigmoid, you have the tanh, the rectified linear units. Depends on time, should I? Yeah, let me do it. So sigmoid, you are classifying between 0 and you are squishing down all your values to a range of 0 and 1. So 0 being usually negative, 1 being positive. Okay, so that you can classify discretely positive or negative. For a tanh, you sort of expand the value so that now it's on a range of -1 to 1. And for the ReLU is actually now the most popular. Okay, ReLU has a lot of advantages in the sense that the tanh function involves some divisions with natural exponents. Okay, that's E is here in your calculator. Yeah. So the calculation for a sigmoid and even for a tanh involves more processing than for a ReLU. What a ReLU does is that you have a straight line when it's 0, and as soon as you hit your threshold value, it just starts to output the actual value, which is a simple if-else if you want to put it in code, as against the mathematical computations that go here. The next thing you need to think about in deep neural networks is regularization. So, because of the complexity and the amount of features that are extracted along the way, what usually happens is that your network will begin to memorize your data set. Okay? So the values that you are getting out of it, they look so good, you are getting 98% accuracy, but then you try it on a real life data set that the model has not seen before, and then your accuracy starts to drop 70%, 80, 60, right? So what we do with regularization is that you are penalizing some of the values that are propagated through the network, so that it doesn't try to rely heavily on certain features that are actually not so relevant to the calculation. So, what the most popular regularization technique for deep neural networks is called dropout. What dropout means is that you drop some nodes in any layer at random. And what that does is that so every pass through your data set is called an epoch. Okay. So after every epoch, you are essentially training a different neural network because some nodes are blocked out. So it prevents the system from depending on any particular node's output um, too extensively. So that by the time you are done, you have essentially ensembled the output of multiple networks, which is going to give you a more generalized output. Okay. So sorry. So dropout is a very popular mechanism. There's also batch weight and layer normalization. So batch normalization in general. So let's say you have an HD picture. You want to identify whether there's a cat in it. Pictures are essentially pixels from a range of every pixel is from a range of 0 to 255. Okay? But your system doesn't need to range things from 0 to 255 to work. You can squish those values down to maybe 0 to 1 and to still be able to predict accurately for you. So normalization is bringing your values, whatever features you're working with, to a reasonable range of each other. Okay, so that no one feature is being measured from 0 to 255, while another feature is being measured from 0 to 1, another is being measured from 5 to 15. You bring them all within a reasonable range. And it turns out that when you do the same thing for the weights that are so when you do the same thing for your batches, for your weights, and even for your layers, you are able to get a more general output from your system so that it doesn't memorize the training set. Okay. And then the final one is mix up. I actually saw a video where Mustafa was recommending this one. Unfortunately, I've not tried it yet. So the curious ones among us, that's homework. All right. So why exactly is this whole craze about neural networks suddenly exploding? Because neural networks were really not popular till maybe 2012. But the truth of the matter is that they came out a lot earlier. There are papers on neural networks from the 1990s and even before. Okay. But what happened was, I've already explained how the forward propagation takes your stuff through the network, and then the back propagation depends heavily on differentiation, the chain rule. So with um, frameworks like TensorFlow, there's a lot of auto differentiation that's already done for you. Okay. Now, if you take a very in-depth machine learning course, you probably find yourself implementing gradient descent and even possibly a small neural network by hand. Okay, where you have to do all the differentiation calculations and propagate them too. But now with a framework like TensorFlow, those things are abstracted from you, and then you're able to put in your data, even possibly get pre-trained or pre-configured models, and then use those to build something that's a little more complex. Okay. So with frameworks like this, frameworks like PyTorch and Microsoft Azure, you are able to do a lot more of those complex things quickly. As you can see, these are some of the languages. Like if you're a hard guy, C++, you can do it in. Python is the most popular. There's now TensorFlow JS even for the web developers. You can do it in Java, even Golang. So frameworks like this have made it a lot easier for us to work on machine learning models. The second thing is the acceleration. The kind of architecture and the kind of hardware that we have now. So here's a fun fact: your smartphone in your pocket has more computational power than the entire NASA during the space landings. Okay, so the computers that took man to the moon, the phone in your pocket, that's more than those computers. And if that is the power that we use to do Snapchat, Facebook, WhatsApp, you can imagine what is contained in Google's um, data center, right? So we have a lot more computational power. And one of the things that has made it so easy to do now is the graphics processing unit. Okay, so a lot of the gamers in the house, your NVIDIA graphics card, the one that makes the FIFA nice, that card is built for parallel processing because that's how computer graphics work. They need a lot of parallel processing to give you the best graphics. It also happens that this neural network needs a lot of parallel processing for, because every line you see on this graph is a computation. Every single line. So you need a lot of parallel processing to get this done. So people figured out very early that if you can take the same architecture here and tweak it a little, you can get it to speed up your machine learning computations a lot more. And there's also cloud computing. So um, sometimes you really just want to get stuff done. You don't have your computer is old like mine. It can't do the thing, right? You can log into something like Google Colab, Google Data Lab. I keep mentioning Google. You can log into all these cloud computing facilities and you have access to graphic processing units, even to tensor processing units. And you generally have more RAM, more resources to work with. So now a lot more people are able to tap into these resources and do more. And then the last thing is the explosion of data. Now that everybody has a phone, everybody has a smartphone, and mind you, these statistics are from 2016. As of 2016, it was said that 2.5 quintillion bytes, 10 to the power 18 bytes of data are produced daily in 2016, 3 years ago. 90% of the world's data was generated in the last 2 years. So all the data in the world, as of 2016, out of all the data in the world, 90% was produced from 2014 to 2016. Every second in 2016, there were 40,000 Google searches. Every minute, 527,760 photos on Snapchat. 4,146,000 videos watched on YouTube. 456,000 tweets. Even 990,000 Tinder swipes. So, essentially, all this data which is available online is now data that can be used to train some model, that can be used to get more insight. All right, because we started off by saying that the data is key. So the data that is made available has essentially allowed us to train better models that can do more things. Okay, and then I left the last point, IoT. So now, just as your hands are to your body, or your limbs, your senses, your sense of smell, sense of hearing, that is what IoT sensors are to AI. Because these are means by which you can extract data. Because before IoT took off as it had, there was no data like temperature unless it was manually inputted, right? There was no data like humidity unless somebody manually inputted it. But now you can have an IoT device that is sitting at one place and gathering all this data every second, which greatly and exponentially increases the amount of data we can collect. And by 2020, that's next year, it's estimated that there will be 200 billion IoT devices. That is 200 billion sources of data, right? So the data has greatly helped us to build better models, better architectures that can do better things. Okay, so some of those architectures, and the list is more extensive than this. There are even things here that I've not touched before. So yeah, if you want to find this online, it's called the Neural Network Zoo. If you go to a neural network, the first thing we talked about, the perceptron, is represented here. A feed-forward network is just the network we know, but imagine it without back propagation. So just feeding forward. There's radial basis, which is another variation of this one. And then the deep feed forward. So deep is essentially when you have multiple layers. Okay. So once we start to go into 2 layers and the rest, we have deep feed forward. And now this is one of the revolutionary networks that came around, the recurrent neural network. Now, if you are a developer, you probably know about recursion. So recursion is like you create a function, the function calls itself until it has achieved what it's supposed to do. So in a recurrent neural network, the architecture in the middle sort of stays the same, and then the data that goes out is sent back in, sent back in, and a variation of that is long short-term memory. I want to talk about these two together. So, for example, I mentioned Google Translate. This is the architecture that Google Translate uses right now, long short-term memory. And the reason is simple. When you have sequential data, so like the way I'm talking right now, okay, yeah, my favorite example, subject-verb agreement. If I want to deal with the verb to have, and I say he, what should follow? Has. If I say he and I add have, there's a problem, right? But if we were dealing with the data, let's assume we're dealing with the data in terms of words, and we're dealing with it like we deal with the first word, we put it aside. So you translate he, then you translate have, and so on. We are going to get a lot of problems with subject verb agreement because the sentence does not, the individual words in the sentence do not make sense on their own. So you put them together in a context. All right. So what these recurrent networks do, and you can see some of them have a memory cell, is that they keep or they maintain state in the network, which essentially gives the data context. Okay. So you want to, let's say, sentiment analysis on a tweet. Okay, you want to know whether this tweet is racist, right? You cannot just assume that every time you see the word black in the tweet, it's a racist tweet. Because what if the next word was bored? You understand? So we need to maintain context, which is what these recurrent neural networks do for us. They maintain some context. And the slides are okay, it's back. All right. So there are some other ones here, like the autoencoder, the variational, denoising sparse. They all have their places. There's even Boltzmann machines and some other more complicated ones. But I want to show you something that we use this all the time, but we don't know. Or okay, some of us know. I can't assume. Yeah. But yeah, like my guy there was. So this is a deep convolutional neural network. Okay. You probably will not see any representation of it that looks like this anywhere else. You're more likely to see cubes. Okay. Now, let's assume that this is an image because that is the primary use of deep convolutional neural networks. It's for image recognition, classification, identifying people in images. And the next layer is called the kernel. So what a kernel does is that it is going to imagine there was a screen on this image about this wide. Okay, you can only see through the screen, and then the screen is sliding across the window. Then it comes to the next line, slides across the window, comes to the next line. That's the way a kernel works. It moves across an image in strides, and it has some. It's a matrix of certain values depending on what you are trying to do. That is going through the image and performing multiplications on the underlying image. And as it does that, it extracts certain necessary features into the next layer of the network. Okay? So as it slides across, it does its multiplication, and then it's looking to. So let's say you want to detect human beings in the image. As it slides across, it extracts maybe edges or the color of your hair or something that makes your image stand out of the rest of the picture. Okay, and then it passes that on to a convolving layer, which further extracts features. So your kernel gets certain basic features from the image, and then as it moves through the network, the necessary features are being highlighted and being extracted, so that when you show an HD image to a computer and ask it whether there's a human being inside it, it actually does not need the HD. It doesn't need all that high definition. It extracts the necessary features, and by the time it gets here, it has removed whatever wasteful megabytes or kilobytes were coming along with it, and then um, it has a more detailed, more an image that is compressed but with more necessary features for recognition, right? Then we pass it back into, we've seen this guy again. This is a normal feed-forward network on which we now perform our classification. So this can be, maybe we're identifying 3 types of fruit. So the first output is um, mango, next is pear, the third is banana. Okay, so now it assigns probabilities to each of them. So maybe this is 0.9%, sorry, it's 90% sure it's a banana, and then it shares 5%, 5% among these. So then we assume that, okay, it's a banana. All right. So that's how convolutional neural networks work. And the reason why I spent time on this one is because this is a major use of deep neural networks. Okay. Um, Analyzing images, extracting information, classifying images is a major use of deep neural networks. And If you go down this path, you are likely to deal with convolutional networks a lot, just as you might with recurrent neural networks. Deconvolutionals do the opposite. So now you've narrowed it down to certain features, but your image has lost detail. You can do the reverse and get more detail on your deconvolutional. There's an architecture which combines the two. So, um, yeah. So, for example, you remember the pix to pix example where we had a cat a drawing and then going to another one. So it's possible that we convoluted the first image, got some output, determined that okay, this looks like a cat, and then extrapolated a new cat image from the features that we got. Okay. And then there are, yes, I like this one. The generative adversarial networks. I like them because they are scary. There was a video I saw of Obama saying four different sentences and apparently he never said them. It was created by a generative adversarial network. So you see the first part here. Okay, so sorry, I should have. So according to the keys, the reds are sort of outputs. Okay, so the first part here is, let's say, a network on its own, and then the second part is also another network on its own of sorts. And the first one is trying, so this part of the network is trying to fool this part of the network. So this one is generating its own output. And based on the output that is generated, this second part is looking for problems in your output. So they are both competing with each other. So as this one finds more problems, this one corrects it, this one finds more problems, this one corrects it, and it goes on until the system is able to produce images and text and videos that can fool you and make you think that um, something is there that was not. Okay, so this is actually an area of great concern because this is a source of a lot of fake news. There was even the controversy about the black hole that was discovered. There was a picture taken of the first ever black hole, and people were speculating that it was created with a gun. So, yeah, this is an area of great concern. And yeah, the rest are, I think I'm spending so much time here. But the rest are also certain variations of all these neural networks, and I don't claim to know all of them. Okay. Okay, yes, support vector machines. I think that is another one that I should talk about. So SVMs, they deal with spatial. Okay. For the sake of simplicity, think of an SVM as something that draws very neat lines. Okay, so you have two data sets, and they are separated into two clusters. The SVM is trying to draw a straight line between the two of them. That is an equal distance from the main components of both data sets. I should have put a graph there to explain better, but uh, you can catch me and I'll draw the graph for you later. Okay. So, all right. So these are a few legendary models, and I say legendary because they served as the basis for a lot of change in the neural network realm. The first is Linet. Linet was made in the 90s, okay, and it was used for handwriting recognition. Okay. So a lot of the handwriting recognition tools that exist now are stuff that were built off of the Linet architecture, and it has 5 layers. Because you see, when we say deep, we are really going to be going deep. Okay, so this is 5. This was deep in the 90s. Then AlexNet came along and it had 8, and that was cool. AlexNet won there's this ImageNet competition that runs every year, right? And it's sort of a platform for CNN researchers to test out their new models. Okay, so AlexNet won, and then another one came called BGG. I think the one that won in 20, I've forgotten the year. That was VGG 16, but this is VGG 11 to VGG 19. So there are different versions of VGG with their own number. So there's an 11 layer VGG, 12, 13, up to 19. Then there's GoogleNet, which is Google's version of Linet, which had 22 layers. And we thought that was plenty. Then came Inception V4. Inception V4, from what I've heard, was named after the movie Inception. Because you see how you enter one dream, enter the next dream. Yeah, there are networks entering networks, entering networks. Yeah, and it has 76 layers. Then there's the ResNet, which has had 34 layers at one time, 152 at another, 1001, and now 1202. Okay, so the depth and these are not things you'll be running on your local computer. Um, yeah, if you like your machine, it's not too safe. You might probably want to run it in the cloud, but yeah. So these networks have existed, and then these two are arguably my favorites. So the YOLO version 3, and YOLO here stands for you only look once. So I explained how, I said look or not look. I explained how the convolutional neural network works. It has the kernel that is sliding across the screen. YOLO does something that's entirely different. YOLO will split the screen into a grid, okay, and then now work on each grid, because the purpose of YOLO is for speed, is for real-time object detection. So it doesn't have time, because you realize that every video you watch is actually frames of still images. Okay, so as you're analyzing the data, you're analyzing the frames. So for every image that comes, especially if you're watching at 1080p and you want to pass this through YOLO, it's going to, if it was using a normal convolutional network stuff, it's going to take every frame, stride across it, try to extract features. But instead, it just splits the screen into grids and then deals with each grid individually, which is a lot faster than standing on the first spot, moving to the next, and sliding across the screen. So with that, it's able to perform like in real time. If you have a system built with YOLO and you are watching a video, it can detect, like as a human being is passing, it detects as a cow is passing, whatever, it detects it in real time. And then the wide and deep was, this one came out like pretty much either this year or early last year. So what a wide and deep network does is that we have, you remember I said as your network gets deep, it begins to memorize the data, right? So a deep network typically will, oh, sorry, where is that? No, sorry, other way around. So a deep network will typically generalize better than a wide network. We've explained what deep is, so the wide should be a little. So deep is multiple layers, so the wide is a single layer. So we found that the wide layers memorize more and the deep layers generalize better. So what researchers have now done is to find a way to combine the two. So you have a network, a deep network that is analyzing your data, and then you have a wide network that is also analyzing your data. And then in the end, they combine their outputs to a single activation function. So that the wide network is helping your system memorize better, get used to this kind of data. And then the deep network is helping it to generalize better, so to do better on unseen data. And that is one revolutionary network that has come up. So case studies, why all the hype about this deep learning thing? And like I said, somebody from DeepMind is in the building, so yeah, I'm glad about that. So what DeepMind did, Shakir's company, is that they built um, something called AlphaGo, which was a model to play the Chinese game Go. I don't know how many of us know that game. So yeah, so Go is a board game. It's very hard. It's very, very hard. And the world champion at the time, he was an 18-time world champion, and he played against this machine. Poor boy. It won him 4 games to 1. Okay. And as if that was not enough, the next year they built a new model called AlphaGo Zero. And AlphaGo Zero did not play against the world champion. He played against the one that beat the world champion. And it won its predecessor 100 games to nil. Okay. So this is not something you do with a decision tree or random forest, or you need to go deep to get this done. You understand? So, and yeah, the impressive thing is that AlphaGo learned from um, the world's best Go players before it played against the world champion. But this one, oh, no, sorry. AlphaGo Zero learned on its own, started from scratch, played against itself. All it was given were the rules of the game. And it played against itself from scratch until it got to a point where it was able to beat its predecessor by 100 games to nil. So I mean, these diagrams here, these various architectures, they are not just research topics that are not going anywhere. These are things that people are actually using to build stuff that can do wonders. That you understand. So yeah, that is why we have all this hype about deep learning. And I'll end my talk with a quote that I heard from Mustafa. I think he gave a similar talk in one in Daba. And the quote is, "Go deep or go home." Thank you.